Good afternoon. My name is Elena Scacchia and I am a PhD student from the University of Parma. We know that turbidity current are strongly affected by submarine topography, and so understanding the effect it exerts on turbidity current is crucial for understanding turbidity current pathway and depositional character. So today, with this presentation, I will show to you how we dealt with this topic through a fieldwork approach. The aim of our study, in fact, is to account for short length scale variability in a well-exposed turbidity section in a topographically complex area. And to do so, we choose the Paretaio Turbidite System belonging to the Marnoso-arenacea Formation. Can you see my mouse, my arrow on the screen?
Yes, we can.
Okay, fantastic. The Paretaio Turbidite System was deposited in the Upper Serravaglian in the foredeep basin of the northern Apennines after a strong propagation phase of an important structural alignment represented by the Monte Castellaccio thrust. The northeast shifting of this thrust led to a transition from a larger inner foredeep to another and narrower foredeep. And the Paretaio Turbidite System represents the first deposits of the outer narrower basin, laterally confined by the Monte Castellaccio thrust, where the turbiditic bed overlapped. This system was previously studied through 6 stratigraphic cross-sections that comprehend the stratigraphic interval from the Visignano mass transport complex that is located at the base of this unit until the Montecchio bed that is a very thick bed that we can see here that can be traced all through the study area. And this previous study highlighted that this system is composed by 6 sand-prone lobes and a relative interlobe. For this study, we focused on the vertical section comprehensive of lobe 5 and 6 until the Montecchio bed. We performed closely spaced stratigraphic log that you can see here in green in the figure, oriented parallel to the main paleocurrent and to the structural alignment. The great exposure of this outcrop offered the opportunity to trace individual bed for up to 2.5 kilometers. And so detailed bed-by-bed section were performed, and we record the bed thickness, grain sizes, sedimentary structures, paleocurrent, and ichnofacies. So now I will briefly describe to you the facies scheme we elaborated for the sandstone bed of the Paretaio Turbidite System that is composed by turbidite and hybrid beds. In particular, hybrid beds, the first 2 types are tripartite bed, and the type 8.2 is distinguished based on the minor amount of mud content, while the type 8.3 is composed by an alternation between clean sandstone and mud-rich sandstone, and so has been interpreted as a transitional phase from high-density turbidite to hybrid flow. Turbidite are composed by type B and type C that are thick-bedded coarse to medium-grained sandstone, and in particular the type B is composed by liquefied unit and amalgamation surfaces, while type C presents at the top traction carpet and mega ripple and are mostly devoid of the fine-grained interval, indicating the action of a strong bypass. While type D and type E are the equivalent of type B and C, but are composed by medium-grained sandstone, while type F, that are contained reflected beds, are principally located in the interlobe. And finally, type G are thin-bedded fine-grained sandstone. So to subdivide the sand-prone lobe that are the principal object of our study, We used the hierarchical approach of Prelat et al., and we recognize that each lobe is composed by 3 lobe elements. Where the Montecchio key bed is present, the correlation highlights that there are subtle morphological high that are here represented by the red arrows, and there is one in the proximal area and one in the distal area. And in the middle, there is a depocenter here marked by the green line. We have seen that they are persistent also in the underlying lobe, and so we interpreted that they are a real topographical variation of the seafloor, probably derived from secondary structure associated to the main thrust. Now I will show to you some close-up of the lobe elements. This is the lobe element 5A, and here with color are marked the different facies, giving an insight on how single depositional event change down current that is towards the right. So with this first flattening, we can appreciate that the thin fine-grained interval thins and pinch out in proximity of the subtle morphological high, and the erosion of the substrate is also highlighted by the presence in log 9 and 11 of substrate delamination features. Interesting are also the numerous variation in the paleocurrent orientation, and here I'm showing to you an example from bed 91 that presents flute cast oriented 130 degree to the north, while the cross stratification in the fine-grained interval are prevalently oriented to 100 degree to the north. This first flattening also highlights that there is another subtle morphological high in correspondence of log 11. And near this position, we can see an increase in mud content inside the hybrid bed that is marked by the facies variation that we can see in the picture and also in the picture below. And the same evidence has been found also in bed 93 and 94. This second flattening includes the lobe element B, 5B and C. And again, here we can see the thinning and pinching of the fine-grained portion in proximity of the morphological high. These lobe elements are composed prevalently by thick-bedded turbidite made by alternation between facies C and B. And now I will show to you a detail of bed 97 between log 4 and 5. In the upper part, we can appreciate the lateral facies and thickness variability over a section 200 meters long. And we can see that where the bed is thinner, it is composed by a massive coarse-grained base and an upper liquefied portion, while where the bed is thicker, above the massive base, there are traction carpet in backstepping, as we can see from the picture below. While to the east, this bed is characterized by the presence of an erosive surface draped by mud-rich sandstone. Let's go ahead with the lobe element 6A, and again we can see the pinching of the fine-grained interval in proximity of the subtle morphological high, and also the amalgamation of bed 109 and 110. Also in this lobe element, some beds exhibit short length facies transition. Here I reported the example of bed 104 that is thick-bedded and coarse-grained in log 5, while it exhibits a short facies transition in less than 450 meters to a tripartite hybrid bed in correspondence of log 7. This is the last flattening that include lobe element B and C that are again composed prevalently by thick bed turbidite made of alternation of facies B and C. So the vertical facies distribution in both the lobe is quite similar and reminds the progradational stacking pattern described by Spiciola et al. In particular, they are composed by basal hybrid bed, followed by medium-grained beds, while the upper portion of the lobe are prevalently composed by coarse-grained beds with water escape structure, bypass indicator, and, as we have seen in bed 97, upper flow regime structures. In particular, we have interpreted that the progressive transformation from type B to C that is prevalent in the upper lobe could represent the downslope evolution of an hydraulic jump, producing a mass deposition, and that is represented by liquefied unit of the beds that sometimes is also highlighted by the presence of an erosive scour that laterally evolve in backsetting traction carpet that represent the reacceleration of the flow. And this facies structure well fit with the evidence, the other evidence found in the field, and with the result of tank experiment.
You have 2 minutes.
Yes, thank you. While the other sedimentological evidence have shown to you tell to us something about how the flow behave in correspondence of the surrounding topography. In particular, the lateral confinement operated by the Monte Castellaccio Trust is highlighted by the paleocurrent deviation of about 20-30 degrees between soil marks that we can see here represented by the black arrows and the ripple cross stratification represented by the purple arrows. This suggests us the rebound of the upper turbulent flow on the surface of the lateral slope, while the abundance of facies with bypass indicator is indicative of the drastic deceleration of the basal dense flow, while the upper turbulent flow is able to bypass. And this condition is quite characteristic of confined setting. And also the high percentage of hybrid bed is meaningful since they are quite common where the flow is forced to decelerate against morphology. We have also seen that the flow are reactive also to meter scale morphology, since we have seen that the fine-grained interval close in proximity of the morphological high, and we have seen also that hybrid bed events increase in correspondence of morphological high, as we can see from the picture to the right, where hybrid bed thickness percentage increase in coincidence of the morphological high, both in lobe 5 and lobe 6. So in the future, we would like to perform tank experiment in order to understand the dynamic of the hydraulic jump in the upper lobe in connection to a lateral confinement and in relation to a previous topography. We will perform the tail grain size analysis in order to characterize the bed and their variation downslope, and we will perform cross-section perpendicular to the paleocurrent in order to understand the lateral short distance facies variation. So thank you very much, and if there are some questions, I'll try to answer.
Thank you very much, Elena. That's a great talk on the Marnoso-arenacea Formation.